sophistication of trumpet design. Each component of the mouthpiece, from the rim to the backbore, works in concert to shape the way air is transformed into sound, demonstrating how the principles of fluid dynamics and acoustics are applied in a tangible, musical context, for musicians and engineers alike. This is a fascinating area where art and science converge, offering endless possibilities for experimentation and innovation in the quest for the perfect sound. Sound production on the trumpet involves the player's lips acting as a valve, vibrating at high speeds to create a buzzing sound. This buzz is then amplified by the trumpet's tubing. The pitch is controlled by both the tension of the lips and the length of the air column, which is altered by pressing valves. The three valves on a trumpet redirect the air through additional lengths of tubing. When a valve is depressed, it opens a pathway that makes the air travel through extra tubing, lowering the pitch of the note being played. Each valve combination corresponds to a specific change in pitch, and through these combinations, a player can produce all the notes in the chromatic scale. The engineering behind the valves is intricate. Each valve consists of a cylindrical casing and a piston that can be moved up and down. The piston has a series of holes and channels that align with the tubing when the valve is depressed. Precision is crucial here. Even the slightest misalignment can lead to air leakage or intonation issues. The valves are typically made from a combination of brass and nickel, materials chosen for their durability and smooth action. The interior surfaces are polished to minimize friction and ensure rapid movement, allowing for the quick fingering required in complex musical passages. The engineering behind musical instrument valves, particularly in brass instruments, involves a sophisticated understanding of both mechanical precision and acoustical physics. The cylindrical casing of the valve is designed with micrometer level tolerances to ensure that the piston can move smoothly within it. The alignment of the piston's holes and channels with the corresponding tubing is a testament to precision engineering, as the slightest deviation in this alignment can cause disruptions in the airflow. This is not merely a mechanical issue but one that significantly affects the acoustics of the instrument. Air leakage through even a small misalignment can alter the pressure and flow rate within the tubing, leading to changes in pitch and timbre. This demonstrates the intricate relationship between mechanical precision and acoustic performance in instrument design, where even minor imperfections can be amplified through the complex resonating body of the instrument. The choice of materials, typically a combination of brass and nickel, is also a deliberate decision that balances durability, weight, and acoustic properties. Brass, known for its resistance to corrosion and excellent acoustic characteristics, forms the primary structure of the valve. It offers a bright, resonant sound that enhances the instrument's tonal quality. Nickel, on the other hand, is often used for plating the piston and interior surfaces to reduce friction and prevent wear, ensuring the longevity of the valve mechanism. The smooth action facilitated by these materials is crucial for executing rapid passages with precision and agility. The interior surfaces are meticulously polished to create a nearly frictionless environment for the piston. This minimizes resistance during movement, allowing for the rapid and precise changes in pitch necessary for complex musical compositions. The polishing process is not merely for aesthetics but serves a critical function in reducing the microscopic roughness that could otherwise impede the piston's movement and introduce unwanted acoustic anomalies. Moreover, the dynamics of airflow within the valve system are governed by fluid dynamics principles. When the valve is depressed, the airflow must be redirected through a different path, increasing the length of the tubing and thereby lowering the pitch. This redirection must occur without causing turbulence, which would disrupt the sound wave's smooth propagation. Engineers must carefully design the curvature and diameter of the tubing to ensure laminar flow, minimizing turbulence and maintaining the purity of the tone. The transition points, where the air moves from the valve casing into the additional tubing, are crafted with smooth, gradual curves to avoid sharp angles that could cause eddies and vortices in the airflow. This attention to detail is essential for maintaining the instrument's intonation and responsiveness across its range. The physics of the valve's motion also involves considerations of inertia and damping. The piston, when depressed, experiences an initial resistance due to inertia, and if the force applied is not perfectly aligned with the piston's axis, it can cause lateral movements, which increase wear and friction. To mitigate this, the piston is often designed with guiding mechanisms that ensure its movement is constrained to the desired path. This precise control over the piston's motion is essential for maintaining the valve's performance over time. Additionally, the speed at which the piston returns to its resting position is controlled by a combination of spring force and the damping properties of the materials used. If the spring is too strong, the piston may rebound too quickly, creating a percussive noise and potentially damaging the valve casing. Conversely, if the spring is too weak, the piston may not return to its position swiftly enough, causing sluggish performance. The damping must be finely tuned to balance these opposing requirements, ensuring that the valve operates smoothly and quietly. The entire valve system, therefore, represents a delicate equilibrium of mechanical engineering and acoustical physics, where the design must account for both the physical properties of the materials and the behavior of sound waves within the instrument. It is a remarkable example of how engineering precision can directly influence artistic expression, as the valve mechanism not only facilitates the production of different pitches but also contributes to the overall tonal quality and playability of the instrument. The integration of these elements reflects a deep understanding of both the physical laws governing sound and the practical demands of musical performance, making the design of these valves a pinnacle of engineering excellence in the realm of acoustics and mechanics. Another critical element of the trumpet's design is the bell. The bell's flare amplifies and projects the sound, acting as an acoustic impedance matcher. This means that it helps transfer the vibrations from the air inside the tube to the air outside more efficiently. The shape and size of the bell influence the instrument's tone and projection. A larger bell can produce a broader, warmer sound, while a smaller bell may result in a more focused, brilliant tone. The bell also affects the instrument's timbre, or the quality of sound, which is why different trumpets may sound distinct even when playing the same note. The trumpet's bell is a fascinating case study in the interplay between acoustical physics and engineering design, demonstrating how subtle variations in shape and material can significantly alter an instrument's sound characteristics. At its core, the bell functions as an acoustic impedance matcher, a critical component that facilitates the efficient transmission of sound waves from the instrument to the surrounding air. This impedance matching is crucial because the dense, confined air column inside the trumpet has a much higher acoustic impedance compared to the open air outside. Without the bell's gradual flaring shape, a significant portion of the sound energy would be reflected back into the instrument, rather than being projected outward, resulting in a loss of volume and clarity. The bell essentially smooths this transition, reducing the reflection of sound waves and enabling a more efficient transfer of energy. The design of the bell is not just about the efficiency of sound transmission, it also directly influences the trumpet's tonal qualities and timbre. The gradual widening of the bell allows lower frequency waves to emerge more effectively, enhancing the instrument's ability to produce a full-bodied, resonant sound. This is why a trumpet with a larger bell can produce a broader and warmer tone, as the expanded surface area of the bell allows for a richer harmonic spectrum. In contrast, a smaller bell, with its narrower profile, tends to focus the sound waves into a tighter, more directed beam, producing a tone that is sharper and more brilliant. This physical shaping of sound is a key reason why trumpet players select different instruments for different musical contexts they're choosing. For instance, a larger-belled instrument for a symphonic setting where a lush, blending sound is desired, and a smaller-belled trumpet for solo or jazz performance where clarity and projection are paramount. Beyond tone and projection, The bell also plays a significant role in shaping the trumpet's timbre, often described as the color of the sound, is influenced by the complex interaction of harmonics produced within the instrument. The bell's curvature and flare determine how these harmonics are amplified or attenuated as they exit the trumpet. A bell with a steeper flare rate, where the diameter increases rapidly near the end, tends to accentuate the higher harmonics, resulting in a brighter, more piercing timbre. Conversely, a bell with a more gradual flare produces a smoother, mellower sound by favoring the lower harmonics. This ability to fine-tune the harmonic content of the sound is why even small changes in bell shape or size can make one trumpet sound dramatically different from another. The material of the bell also contributes significantly to its acoustic properties. Different metals, such as brass, copper, or silver, have varying densities and stiffness, which influence the way the bell vibrates in response to the air column inside the instrument. For example, a bell made of thinner brass will be more flexible, allowing it to vibrate more freely and produce a sound with a richer harmonic content and a broader dynamic range. In contrast, a thicker, stiffer bell, such as one made from silver, will have less internal vibration, resulting in a sound that is more focused and direct. The choice of material, therefore, is a deliberate decision made by trumpet makers to achieve a specific tonal characteristic, tailored to the preferences of different musicians and musical styles. Moreover, the engineering of the bell must also account for the mechanical stresses that occur during play. As the bell vibrates, it undergoes a series of rapid, high-frequency oscillations that can lead to metal fatigue over time. To counteract this, some trumpet makers reinforce the bell with a secondary layer of metal at the rim or employ specific alloy compositions that offer greater resilience. This not only enhances the durability of the instrument but also affects its sound, as a reinforced bell can alter the distribution of vibrational modes, subtly shifting the instrument's tonal balance. The physics of sound radiation is another aspect where the bell's design plays a crucial role. The shape and flare of the bell determine the directivity pattern of the sound waves as they radiate from the trumpet. A wide flaring bell will disperse sound over a broader area, creating a more enveloping acoustic presence, which is ideal for blending with an orchestra or ensemble. On the other hand, a narrow bell directs more energy forward, allowing the sound to cut through other instruments, which is particularly useful in solo or lead playing situations. This directional control of sound projection through bell design is an excellent example of how acoustical engineering principles are applied to meet the specific demands of musical performance. In addition to these considerations, the interaction between the bell and the rest of the trumpet's structure cannot be overlooked. The bell's vibrations interact with the standing wave patterns within the instrument's air column, influencing the tuning and intonation of specific notes. This is why some trumpet designs feature bells with varying thickness or taper profiles, fine-tuning the instrument's response across its range. Such engineering adjustments ensure that the trumpet maintains a consistent tonal quality and precise intonation, whether it is playing in the lower, middle, or upper registers. The continuous refinement of these parameters by instrument makers is a testament to the deep understanding of both the physics of acoustics and the practical demands of musicianship. Ultimately, the trumpet's spell is more than just an endpoint for the instrument's air column. It is a sophisticated acoustic device that shapes the very essence of the trumpet's sound. Its design is a delicate balance of physics and artistry, where every curve, material choice, and structural detail contributes to the instrument's unique voice. This fusion of science and craftsmanship is what allows the trumpet to produce such a wide array of tonal colors and expressive possibilities, making it one of the most versatile and dynamic instruments in the brass family. The bore size of a trumpet is a critical factor that influences not only its acoustic properties but also the physical dynamics of playing the instrument. Understanding how bore size affects the instrument's behavior requires delving into both the physics of sound production and the mechanical aspects of airflow within the tubing. A larger bore trumpet, for example, offers less resistance to the flow of air, which means that the player's breath can move more freely through the instrument. This increased freedom of airflow allows for a broader, more resonant sound, which can be particularly advantageous in settings where projection and volume are essential, such as in orchestral or big band performances. However, the reduced resistance also demands greater breath control and lung capacity from the player, as they must maintain a steady, controlled airflow to avoid producing an unstable or overly diffuse sound. The physical demands of playing a large bore trumpet mean that such instruments are often favored by experienced players who have developed the necessary technical skills and stamina. On the other hand, a smaller bore trumpet introduces more resistance to the airflow, which can be advantageous in different musical contexts. The increased resistance requires the player to exert more effort to push air through the instrument, but this effort results in a more focused and compact sound. The added resistance also provides a tactile feedback that helps the player control the pitch and dynamics more precisely, especially at softer volumes or in technically demanding passages. This makes small bore trumpets particularly suitable for solo or chamber music settings where subtlety and control are prioritized over raw power. Additionally, the high resistance of a small bore can help players produce a clearer, more articulate sound when playing rapid or intricate passages, as the instrument responds more quickly to changes in breath pressure and embouchure. The relationship between bore size and sound production can also be analyzed through the lens of fluid dynamics and acoustics. When air is blown into the trumpet, it behaves as a compressible fluid, and the variations in bore size alter the flow characteristics of this fluid medium. In a larger bore, the lower resistance results in a smoother, more laminar flow of air, which tends to produce a sound that is richer in low-frequency harmonics, contributing to the instrument's overall warmth and fullness. Conversely, in a smaller bore, the increased resistance can cause the airflow to become more turbulent, which can enhance the production of higher harmonics. This interaction between bore size and harmonic content is a key factor in the distinctive timbres produced by different trumpets, and it allows players to choose instruments that complement their unique sound preferences and performance contexts. From an engineering perspective, the design of a trumpet's bore must also account for the structural integrity and durability of the instrument. The tubing material, wall thickness, and bore shape all interact to influence how the trumpet withstands the mechanical stresses of playing, such as the internal pressure generated by the player's breath and the physical impacts that can occur during transport and performance. Larger bores, due to their greater internal volume, may be more susceptible to slight deformations that can alter the instrument's tuning in response. Engineers must carefully balance the desire for a large, free-blowing bore with the need for structural stability, often employing specific bracing techniques and choosing materials with optimal strength-to-weight ratios to achieve the desired performance characteristics. Another consideration is the effect of bore size on the instrument's intonation and tuning. The diameter of the tubing influences the pitch of the notes produced, as it affects the wavelength of the standing waves that are established within the trumpet. Larger bores can sometimes lead to tuning challenges, as they may produce notes that are slightly out of alignment with the standard harmonic series, particularly in the upper registers of the instrument. This requires both the player and the instrument designer to make fine adjustments, such as altering the shape and